Hello, in this lecture we were going to define a new concept, and this is the vector product of two vectors that we will later use for certain concepts in mechanics. So assuming we have two vectors P and Q as shown, we can define the vector product between P and Q as P cross Q. So the vector product is also known as the cross product, and please note the symbol between P and Q, which looks like a small x and which denotes the cross product, the vector product between P and Q. The result will be a vector V, and this has the following characteristics. V is perpendicular to both P and Q, so it's perpendicular to the plane made by P and Q. The magnitude of V equals to PQ times sine theta, where theta is the angle between P and Q. And thirdly, we need to know the direction. And the direction of V, of the vector product of P and Q, is given by using the right-hand rule. So let's see how we can use the right-hand rule in this example. So basically, if we curve our four fingers around the direction of V, which is perpendicular to P and Q, and our four fingers indicate the rotation of the first vector P over the second vector Q, then the thumb will give the sense, the direction of V, using, of course, the right-hand rule. Now, a few properties about the vector product. It is distributed, but it's not commutative, and that means that P cross Q is not equal to Q cross P, and the vector product is also not associative. So in other words, the order in which we perform the operations matters. So in this case, if we cross P and Q first, the result will be different than if we cross Q and S first. So very important to remember these properties of the vector product of two vectors. Now, what we can do next, we can express the vector product between P and Q in terms of Cartesian vector format. So that means we will cross Pxi plus Pyj plus Pzk with Qxi plus Qyj plus Qzk, and let's carry on and expand this cross product. So we will get Pxqx times I cross I plus Pxqy times I cross j plus Pxqz times I cross k plus, it's a long one, Pyqx times j cross I plus Pyqy times j cross j plus Pyqz times j cross k plus Pzqx times k cross I plus Pzqy times k cross j and plus Pzqz times k cross k. Well, this is a long expression, and we need to see if we can simplify this expression further. So let's see if we can figure out what these cross products of the unit vectors mean. So if you take the system of coordinate axes and represent the three unit vectors I, j, and k along the three axes. So you can see that if we cross, for example, the unit vectors I and j, so rotating I over j using the right-hand rule, the result will be k, positive k. And also if we for example, now cross I and k, so we rotate I over k, then the result will be negative j, and so forth. Also, you may easily notice that if we cross the unit vector with itself, the result will be 0, because sine of 0 equals to 0. So now we can simplify the above relationship, and what we can do, we can find out the terms that equal to 0, so where the unit vectors are crossed to themselves. And also I cross j is k, and I cross k is negative j, and j cross I is negative k, and j cross k is I, and then k cross I equals to j, and finally k cross j equals to negative I. And now we can look at this expression and rewrite it again, and in the final relationship we're going to factor out the unit vectors I, j, and k, and what we will get is pyqz minus pzqy times I plus pzqx minus pxqz times j, and plus pxqy minus pyqx times unit vector k. And if you carefully look at this expression and you remember your algebra concepts learned in high school, you realize that this is nothing else than the expansion of a determinant. Remember, a determinant is a table, same like a matrix, but unlike the matrix, the determinant is actually a number, so you can expand the table and obtain a number. So if you reverse engineer the above expression, the determinant corresponding to it will be ijk on the first line, the component of p on the second line, and the components of q on the third line. Very, very important expression that you need to remember, because we will use it extensively in solving the three-dimensional problems from now on. Now, how do we expand this determinant to get the above relationship? Well, there are different ways of doing it. I'm going to show you the one where you factor out the top line with alternating sign, or signs really. So we factor out I, and then we end up with a smaller determinant, py, pz, qy, qz. Now we factor out j, but with a negative sign, times a smaller determinant, px, pz, qx, qz, plus, now we alternate again the sign, plus k times the 2 by 2 determinant, px, py, qx, qy, and then expressing these smaller determinants gives us py, qz minus pz, qy times I, minus pz, qz minus pz, qx times j, plus pxqy minus pyqx times k. And if you compare this to the expression at the top, you will see that the second term has a negative sign instead of a positive sign, and the terms in the parentheses are reversed. So all we have to do is change that sign and reverse the orders of the terms in parentheses, and then we end up with exactly the same expression as above. So that's been demonstrated, and hopefully you know how to expand a determinant, whether you use this method or other methods that you've learned in high school. All of them are okay as long as they are correct. So thank you very much for watching this lecture, and I will see you again at the following lecture.